Today we're going to be talking about is centroids and center of gravities. So what is a centroid? A centroid is defined as a point about which the entire line or area or volume is assumed to be concentrated. If you were to take the object that you're looking at and basically consolidate into one single point, that would be its centroid. It's related to the distribution of lengths, areas, and volumes, and basically you can think of it as its center point of all shapes. And what is the center of gravity? Well, this is defined as the point up at which the entire weight of the body is assumed to be concentrated. It's also known as the center of mass, and it is related to the distribution of that mass. Now, for 2D objects, the centroid and center mass will be the same point, but not necessarily 3D points. So you got this toy. The center of gravity is always going to pull it down. So you can imagine if you took this entire shape and consolidate all that mass into one single point right here at this dot, it's going to be pulling down. So if all of a sudden you had some little torque, something that's pushing it out of the way, it's going to pull, the gravity is going to pull that center mass back, and this is why the little bobble toys always stay upright no matter how hard you push them. So, how do rope walkers always carry long sticks? Well, it's because their center mass is not located. This adds extra weight, which then, because this is bowed down, it actually causes the center mass to be lower, and in fact, sometimes it can actually be under their feet. This is going to give them a better chance of walking across it. And then secondly, they can also use the shifting of that pole left or right, and that can adjust their center of mass as well, and that can cause that to help them with their leaning, and they can push off the stick, and that can cause a lean effect, causing their body to rotate in the opposite direction. Now, if your center of gravity is above your center of force, so like say for a boat, center of buoyancy, it will become unstable and want to fall over. But if your center of gravity is below your buoyancy force, then the object will be stable and it will constantly go around. So center of gravity, or the centroid, is symbolized by this shape. It's kind of the 4-quadrant circle. Is located, now when you locate it, you're going to mark them with it's an X and Y coordinates, just like in math. You know, a 2, 1 or 15, -3. The symbols we always use are going to be X bar and Y bar, and that's just saying these are my locations of my coordinates for my centroid. So example, here's a triangle with a base of 2 inches and a height of 1.5 inches, and its centroid is located at 1 inch, and its centroid in the Y direction is 0.5, so I can put it right here. And so that's what we use the X bar and the Y bar, so it's kind of the example. So that's the centroid, meaning that all the mass and all of this area is located as if it's in one location. Now, if the axis references, a center of gravity's body is always calculated with reference to some assumed axis. In other words, it's always going to assume some x, y, 0 points. So where's 0, 0? So if it's a plane figure, usually you always want to start in the lower left-hand corner. That makes sense. That's what we always use, but it doesn't have to be. It just usually makes sense because that's what we use in math, is we always in this quadrant of a graph. Then we always calculate what is my x over and then my y up. Notice that some centers of mass, the centroids, are not on the actual physical object, like this one. It is not located there. It can actually be in the middle. A donut centroid is exactly in the middle of a donut, and it is not concentrated. All that mass is concentrated in an imaginary spot, so it's not its physical location. Now, axis of symmetry. If an object has symmetry, then the centroid will be located at the intersections of symmetries. So if you're a square, you just take your symmetrical, so you cut it in your coordinates, and then there's your centroid. If it's a circle, you can do multiple diameters across, and then located in the center. Okay, we can also do, like, for instance, rectangles, which you talk about. I-beams is located right here in the middle. single C channel, we're giving at least 1 point of symmetry here. So we know it's along this line. We don't know where it's at. It's going to probably be somewhere around here. And this T channel is again on this line. So some of them, it only gives you one axis of symmetry, or if it gives you more than one or two, it can actually tell you exactly where that center of that centroid is located. Now, some centroids are given as shapes, or are given as an equation, and you can easily find it. So I want you to write these down. You can even draw the shapes so you know where they are. So a semicircular arc, so a half a circle. Its centroid is always going to be located in these. You'll need to know these equations. So the length, L, is just pi times r. Its area is pi r squared in half because it's a half a circle. And its centroid is always going to be located a radius away from, let's say, the edge point. So we're always measuring again from that bottom left-hand corner. Its radius, which makes sense because it's an axis of symmetry. Its y location though is 2r over pi, and that one you'd have to calculate, and that would put it right here. Rectangles. Rectangles area is base times height, and its axis is halfway up its height and halfway on its base. It's really simple, and squares also happen to be that as well. Triangles. Area is base times height divided by 2, so 1/2 base times height. And its axis is always a third of it. So we're always looking at a third of the base and the third of the height. And that puts that at their axis of rotation. Circles, again, it's always just the radius. And so it's just the radius of the up and the radius over. Now, what happens if you have a shape that is not regular? It doesn't follow those previous shapes. Well, we can actually use these equations here to calculate any irregularly shaped objects. So we're going to talk about this. This is the sum equation. So we have to first figure out what this equation, this symbol, this means the sum, it means to add up. So we're going to add up all the locations of the centroids of all these different centroids that make up this shape times the area divided by the sum of all of the areas. Well, let's go through that. So first, we have to determine the reference angle, axes. So we're going to say it's right here, this black dot, bottom left-hand corner. Then we're going to take our complex shape and divide it into regular shapes, shapes that we can deal with. Then after that, we can then start using these equations. What we're going to do is we're going to find the areas of our simple shapes. So we know this shape is a 3 by 3, so we can just do it. 3 times 3 is 9. This shape is 3 by 3 again, but it's half that, so because it's a triangle, so half 3 times 3 is 4.5. And we got a rectangle 3 times 6, it's just 18. Then we're going to determine the centroids of each of those locations. So again, this is 3 by 3, so it's just halfway. And this is 1/3 and 1/3, half and half, again, locations. So we put the actual XY coordinates on it. So I give my coordinates 3 and 1, but we have to then take those references down to this point. So determine the distance from each simple shape centroids to the reference axis. So from before, we just had these numbers. Now we have to take it to this. So this one gets a little longer because now it's 4.5 because you added the 1, you had this 3 plus a 1.5 here. So you have to add those reference points, and the same thing from here to here. And you had to add this 6 to this distance as well. Now, we're going to put it into this little calculator that helps us out. You're going to multiply each of the simple shapes areas by its distance from that centroid. Now we're going to have to do it for x and y. So we take the area of our small square times 1.5 equals 13.5. Take our distance from the triangle, or sorry, and then we keep going through every single one of these. So you multiply the areas times their locations, and then we multiply them out. We do the same thing again. The areas stay the same because it's the same triangle, triangles, rectangles, and squares, but the distances are different. Then we sum up those. We add them all together. So we just sum up all our area, and we sum up all the summation, or the products of our x times our area. And we do that again for our x and our y's. So now, once we have the sums of our areas and our sums of the products of areas times our centroids locations, then we're going to take it and divide those two numbers together. And that comes as 85.5 divided by 31.5, which gives us a 2.7. And the 85.5, again, divide by the 31.5, and we locate it. And again, we see that it follows along our axes of symmetry, which makes sense. That should. And that is how we find the centroid of any irregular shaped object. Now, we can do another method, which is called the subtractive method. The subtractive method is very similar to that, but we're going to take out an area. And so it's the same process, but instead we're going to subtract out the areas. So we're going to use a negative areas. So again, we have one big shape, the big square, minus the little triangle, which has a negative area, which is the important part. We find this, again, determine the centroids locations right there, 3 and 3 and 1 and 1. We make it reference to the bottom left-hand corner. So instead of 1 and 1, we say it's now 5 and 5 because we're adding in that shape, so that distance there. Then we multiply each of the simple shapes, but this time we only have two shapes, the square and the triangle. 36 times 3 gives us that number. Negative, and this is the important part, negative 4.5 times the 5 gives us that number. And we do it again for the y-axis again as well. And notice that this is going to be negative. That's important. We need to keep our negatives. Then we sum up our areas. Again, notice 36 plus our negative 4.5, 31.5. And then our products, we sum these up again. 108 plus a negative 22.5 gives us this number. And again, we have the same on that. Then we take the fraction of those, and that gives us our exact same location from our previous one. For the addition, it just might be simpler to subtract than to add. It just depends on which has the least amount of shapes. Now, common structural shapes are these. Steel's properties are designed specifically laid out in the Institute of Steel Construction. When it comes to sizing, we're going to look at these structures, and their structures should always be involved. So we have L's, double L's, T's, we have C's, we have this longer C, we have pipes, round, square tubing, we got the flanged, we have the I-beams, the H-beams. These are all within the civil engineering, deals with that, and you have to take into account of those shapes. So I look at these, and how would you find the centroids for these ones? I want you to list them in the program, and I want you to list it, additives versus subtractive, and then separate them by commas. So you should have 5 answers. And there's this one. So I would have done this one. I could do as a additive with a subtractive circle. You could do it both. This one, I would do it as an additive with 3 rectangles. Definitely additive on this one. You could do subtractive on this one. You could just subtract the material out of the I-beam. Same with the middle of the C. That would be a lot easier. You could have just one square with 2 sections there. This one would be a big shape with a little missing there, and then this one would just be definitely subtractive. So if you have any questions, go ahead and ask your teacher.